Optical and structural characterization of AlGaN films deposited by reactive sputtering, using targets prepared with powders synthesized by pyrolysis. Introduction. III-nitrides are considered materials very important for applications to semiconductor devices. Due to their emission energies with wavelengths from the blue band to the ultraviolet band, 470 nanometers to 300 nanometers. GaN, AlGaN, and IN compounds generally crystallize in the stable phase as wurtzite structure and the metastable phase as zincblende, with a wide band gap, and values of 0.79 electron volts for IN, 3.4 electron volts for gallium III-nitride, and 6.2 electron volts for AlGaN. Besides, III-nitrides have their main applications in optoelectronic devices. However, in the last years, they have also been used to manufacture batteries for pacemakers and biosensors. Particularly, the AlGaN alloy has outstanding properties, mainly mechanical, electronic, and optical. On the other hand, the main methods of thin film growth of AlGaN alloy are MOCVD, MBE, and sputtering. The AlGaN alloys have applications in devices such as light-emitting diodes, laser diodes, and solar cells. In addition, the AlGaN alloy has shown the presence of nanostructures with possible applications to biosensors. Currently, the reactive sputtering technique using prepared targets has gained importance in the III-nitrides deposition. Industrially, the production of AlGaN films by sputtering is done using different sources, such as gallium oxide, which is used as a gallium target, aluminum, ammonia, and nitrogen. On the other hand, only AlGaN, or GaN targets can be found on the market, but in particular, the AlGaN alloy does not exist commercially. This work presents the obtaining and characterization of AlGaN films by a reactive sputtering technique using targets prepared in the laboratory, where the solid fraction X is 0.6. The experimental process can be divided into three main parts: powder synthesis, balance the reaction equation for obtaining AlGaN by pyrolysis, which is equation 1. Using this equation, calculate the moles and grams of the reactants to be used. Inside on a fume hood in a Teflon baker, add 20 ml of toluene, add the aluminum nitrate and the gallium nitrate. On a thermomagnetic stirrer grill at 111 degrees Celsius for 15 minutes to dissolve the reagents, add the carbohydrazide to the mix and keep it for 20 minutes at 111 degrees Celsius so that the toluene evaporates until a viscous compound is obtained. In the muffle furnace in an air atmosphere, the viscous compound is distributed in alumina cores, starting the pyrolysis process at 180 degrees Celsius for 20 minutes, subsequently increasing by 1 degree Celsius per minute until reaching 400 degrees Celsius and obtaining a powder. The next step is to grind the powders, store them and be able to carry out the nitriding process. The nitriding process was carried out in a 3-zone CVD furnace, with an ammonia flow of 100 SSCM for 1 hour. The obtained powders were stored and characterized. Obtaining targets. The targets generation process begins with the compaction of the powders into a 1-inch diameter tablet approximately 5 mm thick with an industrial press, applying a pressure of 10 tons. Sintering was carried out in a CVD furnace at 800 degrees Celsius in nitrogen flow for 1 hour, and this process was repeated until obtaining the necessary hardness to use the targets in sputtering. The targets were stored, awaiting deposition by sputtering and reactive sputtering of the thin film. Deposit of thin films. Currently, the sputtering deposition is awaiting since, as a consequence of the pandemic by COVID-19, the equipment presented malfunctions, which is why it underwent a maintenance process. The conditions proposed are the following. Silicon and quartz substrates will be introduced. The deposit will be made with a flow of nitrogen, and later another deposit will be made with a flow of nitrogen and argon. The growing conditions of the films will be 50 watts power, 25 millitorr vacuum pressure, 8-hour rise time, and distance between substrate and objective of 40 millimeters. Once the thin films have been obtained by sputtering and reactive sputtering on the substrates, the morphological, structural, and optics. Conclusions. The AlGaN and AlGaN powders were obtained through the pyrolysis route in a muffle furnace starting with an approximate temperature of 180 degrees Celsius for 20 minutes. Subsequently increasing 1 degree Celsius per minute, until reaching 400 degrees Celsius in an atmosphere of air. Nitriding was performed using a 3-zone CVD horizontal furnace at 1000 degrees Celsius for 1 hour at atmospheric pressure with an ammonia atmosphere. TGA and derivative TGA shows that the polymer decomposition process is a one-step process at 286 degrees Celsius and is exothermic. In the XRD characterization of GaN and AlGaN X equals 0.6. The characteristic planes of the crystallographic chart coincide, but in AlN additional peaks are shown that are thought to correspond to the incorporation of oxygen and carbono. SEM shows that the material has a porous appearance. It is expected that with TEM the growth of nanocrystals can be corroborated. With XPS, the generation of the ternary alloy of AlGaN X equals 0.6 is confirmed, as well as the incorporation of unwished oxygen and carbono impurities. With the EDS characterization, the high levels of oxygen in the material are confirmed, as well as the incorporation of carbono due to the pyrolysis route and the nitriding time. According to the project schedule, GaN, AlN, and AlGaN targets for sputtering are currently available. The growth of the thin films by sputtering in the BUAP is awaiting, since due to the non-use due to the COVID-19 pandemic, the device presented failures that are being solved with maintenance. Thanks.